think others can do it.
Okay.
Unless you are in the same domain.
Well, you're now being recorded for the archives.
Yes.
Okay. Very good. And I guess you can stop underways, or how do you want to run it?
Feel free to ask questions along the way. If I see that we are getting short on time, I will try to stop maybe the questions and then pick them up later. That's fine. Yes. So I guess I can start then.
Yeah.
Good. So what I want to talk about today is what at least I call the standards landscape. There is a lot of different standards being used in this space. Some are used by PCA, some are used by others, and it might be difficult for those that aren't far into the details to really know what the differences between them are. So what I want to do today is to give a very high level walkthrough of the different standards, not at a technical, from a very technical perspective. And then after that, I want to go through the a practical example that shows how at least some of these relate together. Let's see here if I can change there it works. Yeah. So as you can see, there's some different standards that we'll go through today. There are more standards that could be relevant to present here, but the list was already getting pretty exhaustive, so I decided to leave some of them out. But if there's any specific ones that you feel should have been here, then just please make a note of that in the chat. So with that said, let's go through at an overall level the different standards that we have within the landscape that we're operating in. We have what many people know of as ISO 15926, but then we have the part 4 of this standard. And the purpose of the ISO 15926 part 4 is to basically enable a consistent description of process plants. And for those that don't really know what that means or what the part 4 does, you can think of kind of like an encyclopedia of industrial terminology and classifications for the process industry. And then a lot of people have probably heard of what we call the PCA RDL. And one way to think of that is to think of ISO 15926 part 4 plus several extensions to that PCA has suggested and built up over the years. Another standard that is very important in this space is the Industrial Data Ontology, IDO. This is a standard that's in progress now. It's going through the ISO process to become part of something that's called OBI. But the purpose of IDO is to provide a common way of referencing or describing data across sectors and domains. So if you look at it from more like the ontology perspective, people refer to this as an upper ontology. There's one way to think of IDO in layman's terms is to think of it kind of like instructions for how to make an encyclopedia for a specific industry domain. So for example, ISO 15926 part 4 was an encyclopedia. IDO is the instructions for how to make an encyclopedia. And for those of you that are interested in history, it's worth noting that IDO is an ancestor, I guess, of ISO 15926 part 14. So part 14 was before, and now one is trying to make IDO, or not trying, but we are creating IDO based on the lessons learned there as well. Another standard that I hope everyone here has heard of before is SHIFOS. And let's say the overall purpose of SHIFOS is to make information handover in capital projects easy for people and to make it consistent. And you could think of it kind of like an inventory list of what information to collect and which information to hand over. One important point with respect to SHIFOs is that SHIFOs is more than what people normally refer to as SHIFOs. People talk about the SHIFOs RDL and they say just SHIFOs. The SHIFOs RDL is just the reference data library part of SHIFOs. But SHIFOs has a lot of other documentation, requirements, guidelines, and so on, other than just the RDL. And then we have IAC, CDD. I haven't written out what the abbreviation CDD stands for, but it stands for Common Data Dictionary. And the purpose of IAC CDD is to provide common definitions of components, systems, and other things across several engineering domains with a specific focus on instrumentation, telecommunications, and the electrical domain. And again, here you can think of this as well as an encyclopedia of the terminology and classifications for those fields, mainly for electrotechnical and industrial automation. Then we have another standard called the NOSOC standard. And the purpose of this is at the high level to ensure safe, efficient, and cost-effective projects in the Norwegian oil and gas sector. And one way to think about it, at least from my perspective, is a rulebook that helps you design, build, and operate facilities, co-create, and that rulebook is co-created by the industry. Mm. And of course, if you're deep into the details for each of these standards, the stuff I'm saying might not resonate with you. But again, I want to stress the fact that this is a very high level description of the different standards. We have the DEXB standard, and the purpose of DEXB is basically to make systems engineering topologies and objects more compatible between different tools. You could think of it like a recipe for how you could recreate engineering topologies another place than where it was created. The DEXB Association has a broader purpose. They're working on something called a DEXB Plus, but currently, at least from my point of view, their focus is mostly on the PNID part. And then we have automation ML or AML. That's another standard where the purpose is to enable data exchange and integration across engineering tools within industrial automation. And one way to think of that is kind of like a shared workspace for automation systems. AML itself isn't a shared workspace, but you can think of the dialogue it creates or enables as a shared workspace. And then lastly, we have what we normally refer to as IMF, which stands for Information Modeling Framework. And at a very high level, you could say that the purpose is really to enable a data-driven asset management, which you can do iteratively through the entire life cycle. So you enable people to define the asset as at a very high level, not with many details, and then they can iterate over that throughout the asset's life cycle to enrich it with more data. And one way to think of it is kind of the legacy system, but for an asset, because it gives you the ability to create building blocks, which you can piece together and then create something bigger. One thing that's referred to a lot of times is what we call IMF types. And you could think of those as reusable structures that you can use for classification. That might not say very much to everyone, but we're going to look into that shortly. Any questions so far or comments? Those are welcome, of course. Going once, twice, all right. So there's a lot of different standards we've mentioned here, and I guess some of them at least when you talk about them from a high level perspective, they overlap. And they do in some sense, but I just want to make a point that they do address some different perspectives. So one comparison I've done here is to basically make a difference of the standards that focus on the structural parts, and then the standards that focus on the semantic part, which is defining more the common way of understanding things. If we look at IMF is purely a structural part. It enables you to create models, structured information models, but it doesn't really give any meaning by itself. And then you have AML and XP, which does that, but also adds a semantic element. And then as you see, IDO, the SHEPOS RDL, ISO 5096 Part 4, and IEC CDD is on the more the semantic side. They do, of course, have structures within them, but the purpose is to enable a common semantic understanding of some concepts. So with that said, that was the, I guess you could say, the dry part. Now we're going to look into a more practical example. I'm sure many of you have seen this picture before, or variant of it. And what it basically illustrates is the life cycle of an asset today and what happens with respect to the data management related to it. So today, there's a lot of documentation produced, and some of it is recreated when you go into a new phase, and over time it builds up to a large stack of documents, which is very difficult to manage, basically. And within disk, what we want to do is to still enable the same life cycle, but streamline it so that you have a data foundation, which you then can build onwards on, and then iterate over throughout the whole life cycle. And the purpose of that is that you then don't recreate stuff, but you build on it instead. The practical example we look at today is basically during the start of this life cycle. And full disclaimer here, I'm from the IT side. I don't know these processes in detail, so it might not be 100% correct from your perspective, but bear with me. So if you look at the very start of this life cycle, you could say that, or you would have to say that an operator sits down, defines a need and some purpose for a project. And then they take that and they send it to an EPC. Of course, again, this is a high-level summary of what happens. But they send this to an EPC, and then the EPC takes that and they start by creating a block flow diagram. And if I understood you correctly, Jan, the one thing that's done after that is to conduct a heat and mass balance. And then after that's been done, the EPC creates the process flow diagram.
Yeah.
So that's the overall workflow we're going to focus on in this example.
Mm.
The first step after the need and purpose has been defined is to create the block flow diagram. So to do that, most likely one makes use of some basic drawing tool that enables any kind of diagram. And you could say that you produce a diagram that looks something like this. Of course, it does look different in reality, but the structure and level of detail is something like this. After that's done, you export this diagram as a PDF, and then you conduct the heat and mass balance, and you create, there's a type on there, it says create PDF, but you create a PFD in another tool. And after that, you have to export that again as another document. So then the question here is, how can we improve this with IMF? And it's very important to understand that I'm not talking about improving the workflow itself, but I'm talking about how can we improve the data management part of this with IMF. This slide here, this shows the block flow diagram, but just with IMF. It's not 100% correct, but this is what a IMF model could look like that presents something like what we saw earlier. At the top part, we have the offshore platform system, which is described as a overall block, you could say, in the function aspect. And then you have different parts beneath that. You have a gas treatment unit, separation train, oil stabilization, and you have a storage system. And those parts again, those units again, have different terminals that define what goes in and out of them. And you can also see here that there's some information about how these different units and terminals are connected together. Now, if you created this block flow diagram in a tool and that was integrated with IMF, you could produce this model. What would happen then when you were going to create the process flow diagram at a later stage? Basically, you would extend it to add more detail to it. In this case, I've just added some details about the different temperature and pressure thresholds that the different terminals would have to withstand. So these are functional requirements that the EPC contractor would add, which then would be reflected when they go out and look for different equipment to satisfy this. One important question in this context is, how do we stay consistent? So if we use IMF, okay, we can represent these diagrams that we have, or the work that the asset that we are constructing as a model, but how do we ensure that that's done in a similar way across different projects and different organizations? One of the important factors there is to make use of what we call IMF types. And in this example, I've just highlighted one part that could be an IMF type, storage system, which describes which terminals it has, so on. But if we take a part out from the PCA library services in production today, we can look at an actual IMF type. As I've mentioned before, IMF types are, you could look at it as reusable blueprints. So then if you think back to the Lego analogy I've used earlier, IMF types aren't the Lego blocks themselves, but it's a blueprint of what a Lego block should look like. So that is what an IMF type is, just in this context. So this example here shows a differential pressure switch. It has a lot of attributes. I haven't included all of them. And then it also has some subparts. It should have an instrument housing, manifold, and sensing element. An IMF type, when you make use of it with respect to the actual data it has, is, I guess, a set of rules. It's called shackle rule, but when you fetch an IMF type from the PCA library services, what you really get is a description of the requirements that you have to fulfill in order to be classified as something. And that's very useful when you are creating IMF models, and you want to make sure that they are described in a consistent manner from time to time. For this example here, the actual IMF type actually looks like what you see on the screen here. So as you can see, there's a lot of details ingrained in this, and it saves people from doing a lot of work if they had to do this manually every time they were going to define such a model. Again, please stop me if there's questions. So one question that I'm guessing people have is, what do you get from using IMF to improve the data management. The most obvious one, which we looked at in the intro to this example, is that you're able to continue building on the same base. Of course, you have to have a system to do data management, but the structure you create is something you can keep building on throughout the life cycle. Also, an important part here is that IMF isn't something that necessarily has to change how engineers work. If you have the engineering tools integrated with IMF as an underlying foundation, then the engineers can keep doing the work they're doing today in the same tools. And lastly, we have the part about interoperability in general. When you do achieve seamless exchange of data between systems internally and also between organizations, and the data you send is interoperable, so you have the same understanding of it, then you open up for a world of possibilities. There's a lot of new stuff that can be done and tested out, both in large or small scale, whichever is suitable. And lastly here, some of you probably have the question about the other standards. We went through a lot of standards today. So where do those come into play? So far, we have just looked at IMF. I'm not going to show all of the standards, but I'm going to pinpoint some of them now. So this is what the process flow diagram could look like to some level of detail. And if we zoom in on a specific part of this, we can see how the other standards that go on the semantic part are being used. So in this case, I've circled out the output oil terminal. If we look closer at that, we see that it has some requirements about which temperature and pressure threshold it has to withstand. And of course, for us, when we read this, everyone knows what temperature is. We can see that it's 60 Celsius and the pressure is 450 psi. But when we send this between applications and computers, this isn't as obvious. So what we then have to do is to link these up with common descriptions of them. And for the pressure part here, we have, for example, a term definition in PCA today. It's in production. You can go look at it if you want to, which is a RDL term from the Schifos RDL. So in this case, we could use a Schifos term to describe pressure. For the temperature part, we could use a term from PCA's own RDL. And if we look into the Celsius part, we could also describe that with a term from PCA as well as the pressure part, the PSI part. So with that said, that's all I had today. There is probably more information that should be included here, but this is the start. I see that Brendan has his hand raised.
Yeah, thanks for the presentation. One area that I'm really interested in is how we map between these different standards. The example that you gave there, say for instance, for temperature, you had a reference to PCA, and for pressure, you had a reference to CFOS. But each of those standards can most likely map to each other as well. So, and in our world, we call that a corresponding identifier. So, you know, we have an internal code for a class of pump or centrifugal pump, and we have a CFOS class, and we have a PCA ID. That effectively opens up the concept of interoperability. But what it also does is that it provides support for people that are maybe more interested in a specific standard. Say, for instance, CDD, that if we have mappings across to other standards, then we can speak the language regardless of the standard that we're using. Not sure if I said that very clearly.
No, I think it's completely understandable. So it's like you said, there's one way of doing it is to do the mapping internally in the company. Another way is to build that mapping into the reference data itself. And today we have some mappings, but I also know that, for example, I guess you can provide better details about that, Jan, but you have some mappings internally in Aker Solutions to handle this, right?
Yes, we do. We have historical information, and I guess that is what you are alluding to, Brandon, as well, because there is preferences here, historical preferences, that some company used this standard, some other companies used another standard, and now getting this kind of libraries and the connection between the standards can help us make a richer representation of the data with meaning. And having the good work that PostCesar and the MRail group have done together with Skifoss people, CDD people, and other to map and quality check that the references is correct is very valuable.
But it's one of those things where we have, I think, lots of cross-mapped groups of reference data
They do.
that are there for specific purposes.
Yes.
To be able to bring them together into a single library and consolidate them.
Yeah.
It gives you that opportunity to, if somebody wants to use CDD, they can.
Yeah.
And if there's something missing, it's just about adding what's missing and mapping it to the other standards, and then we open that door for interoperability.
Yeah. And I support that 100%, Brandon. And if you look at the DEXB standard, and for that matter, the Skifoss standard that got the library from PostCesar back in the 90s, early 2000, then we now are able, with our computers and data and the power in the cloud, we can make this connected and give a huge value to a larger audience and larger assets, other type of assets as well.
But it's my understanding that we have a lot of this cross-mapping in the old 15926 RDL browser.
Yeah.
And what's always tricky is how can we make that available to people?
Yeah. Yeah, it's a good thing, but you saw now indications of it in Fredrik's presentation here already, because it is there in the IMF types now, and they are used.
For those parts where there is a mapping, and then that's included in the data. So then let's say that you have a reference in the IMF model to some term, and then you can go look that term up, and that term will also give you information in it about, I have an exact match, or I have a close match to this and that, and so on. So it's ingrained in the data for the data points that have that in them.
Okay.
Any more questions? As mentioned, comments too are very, very welcome.
Very good, Fredrik. I think
Very
this
good.
can also be used by others if they need to get clarity around this. It's now we have it on video, so we can distribute it. I will put it in the link when it's finished, so you can use it. Very good. That's what we had. So I see people are leaving, so that means that the meeting is over.
Okay, thanks everybody.
Thank you very much. Thanks.